In this demonstration of a digital medical assistant, we start with our empty database on the left and our user interface on the right. To begin, we need to register a care provider to act as our doctor. When this registration is complete, we can see our first instance of our care provider vertex, along with the corresponding unique event vertex. Each event has a timestamp and holds the identification data for each actor in an event. To continue our process, a patient needs to be registered. Upon registration, a new vertex is added into our database to represent our patient. This is accompanied by another unique event vertex that is related to our patient. Now that both our patient and care provider are registered, we can have our care provider log in and select our patient based on unique identification or a medical record number. Once the identification is verified, an appointment event has occurred between the care provider and the patient, and a new event vertex is added into our database and related between the newly added vertices to represent our acting care provider and patient. The care provider is now able to access the data associated with our patient and is now able to take note of the current symptoms our patient is experiencing. Once those symptoms are entered, they are represented in our database as new vertices and related to our patient. As this process takes place, those same symptoms are sent to a knowledge acquisition process which uses LLMs and historical medical knowledge to hypothesize possible differential diagnoses. This hypothesis generates a new event and enters the hypothesized diseases as new vertices in our database. These diseases are related to the acting symptoms of the event, which indicates the possible disease diagnosis. As our care provider is presented with the differential diagnosis, they can select a disease to gain further insight. Upon this selection, the care provider is given a short synopsis of the disease, as well as a list of other diseases that are statistically significant based on our historical data. Each of these diseases are provided along with a p-value and a list of correlating symptoms that might also be present or become present as the patient's condition progresses. From this screen, our care provider is able to inspect key symptoms and risk factors to reinforce their decision. As key symptoms are generated, the results are added into our database under a new event and related to the relevant disease in which these new symptoms are key to determine a diagnosis. Our care provider can also generate risk factors based on the disease selected. These risk factors are then added into our database under a new event and related to the corresponding disease. If our patient exhibits any of these risk factors, those risks are related to the patient to further enforce a diagnostic decision. If they are sufficiently convinced, they can officially diagnose the disease. Upon diagnosis, a new event is created between the care provider and the diagnosed disease, and another event is created between the patient and the diagnosed disease. Each acting entity is related vertically to events in time and as well as related horizontally through time to show the progression of the network state. These events create trees of related data that can be queried and traversed to recall past states of the network. The data network that is produced can be viewed through two perspectives, as the event history and as an associative memory.